All right, so we're going to continue talking about probability. We're going to look at what's called conditional probability. Okay, so here's what conditional probability is. Conditional probability is this situation. I'm going to find the probability of an event E2. Okay, this little subscript, the E2 means the second event. Okay, that's all that notation is meaning for you. It's not a power or anything like that. It's just saying it's different than E1, which we're going to see. So the probability of event E2, the second event occurring, given that an event E1 has already happened, is called the conditional probability. So what that means is I'm going to find the probability of a second event happening when it's given, when it's known information that a first event, E1, has already happened. The notation for conditional probability is given right here. We still use P for probability, but we're finding the probability of E2, the second event. This bar, when you are reading it, that bar right there is read as given that E1. Okay, so the probability of my second event given that my first event has already occurred. There's a famous probability problem called the Monty Hall problem. I don't know, you probably have never heard of Monty Hall. He was the original host of Let's Make a Deal. Has anyone ever watched Let's Make a Deal? They've restarted it with, oh man, I remembered his name yesterday. I can never remember that guy's name. It's from Orlando. Anyway, it'll come to me later. That's not important. But the problem is this. If you're not familiar with Let's Make a Deal, a situation that's common is you look out at the stage and there's 3 doors, okay, and there's prizes, and they ask you which one do you want. You say, okay, I'm going to pick door 3. Now, before they reveal, they ask you, okay, you're pretty sure about that? Yes. Well, what if I said, I'll give you a second choice and you can, instead of taking 3, you can take one of the others. And so it's based on probability. And the question is it to your advantage? Okay, when they have said, do you want to pick again? Is it to your advantage to pick one of the other 2 doors? Does your probability go up or not? It's actually a highly mathematically contested problem. Math, if you ever take a history of math class, there's so much conflict and fun stories in the math world. Anyway, all that to say, it's all based on conditional probability. That's just it's a more complicated conditional probability problem. So here's my example that I'm going to do. A single card, so we're just drawing one card from a deck of cards. We're going to determine the probability that it's a club, given that I know it's black. Okay, so we've drawn the card, maybe we've shown it to a friend, and they've said, okay, it's a black card. Now I want to know, with that information known, what's the probability that it's a club? So let me write down the notation. I'm finding the probability of a club, given, that's what that bar means, given that I know that it's a black card. Here's the only thing you have to know to be successful at doing conditional probability problems in this class. Again, it can become a more complicated thing, but we are just doing a survey, so we're keeping it nice and simple. Here's what you got to remember. Our probability is successes divided by totals. Success divided by total. Well, now the given information, this becomes your new total. That's all you care about. The given information becomes the new world that you're worrying about. Okay, so when I go to find probability of this, the probability of a club, given it's a black card. Well, what's my total number of outcomes? How many black cards are there? Okay, so that's going to be my denominator. Whatever the given information is, becomes your new denominator. That's your new total number of outcomes. Out of those 26 black cards, okay, so I'm only considering those ones. Out of those 26 black cards, how many of them are clubs? 13. And when you pop that in your calculator, 13 divided by 6 becomes 0.5. In normal probability, the probability of a club is 13 out of 52, 0.25. So you can see if you have some given information, your probability changes, it goes up. So I would like you to try example 2. Just to remind you, because this was a question in my class yesterday, I know it's not this way when you're playing cards, but in this class, we are considering the ace to be the same thing as the 1. Okay, so ace is 1. It's a number. We're counting it as a number card. Okay, so in my deck of cards, I'm trying to find the probability of an ace, given that it is a number card. Okay, well, my number cards now are my total number of outcomes. How many number cards are there in the deck? 40. There's ace through 10. There's 10 cards in each of the 4 suits, so that is 40 cards. Out of those 40 cards, how many of them are aces? 4. So that reduces to 1 out of 10, or in your calculator, 0.10. Example 3, you are going to use those circles. Okay, there's circles with various colors filling them in and then various numbers. So what you're going to do is you're going to do those 3 problems based on that. The first problem is not a conditional probability. It's just a reminder of regular probability. And then the second 2 are conditional. Give it a try, please. All right, so in this drawing, the first one's not a conditional probability problem. So I want to find the probability of a 5. Okay, well, first tell me, what's my total number of outcomes that I have on this problem? There's 6. Okay, we're considering everything. And out of those 6 outcomes, how many of them have a 5 on them? 1. Great job. That's just regular probability since day 1. The next one is the probability of a 5 given that it's orange. So I'm changing it a little bit. So now I am just limiting myself to these 3 circles, the orange ones. So I've just given the way of the answer. What's my total number of outcomes here? 3. I only have 3 orange circles. Out of those 3, I don't care about any of the other circles now. I only care about these 3 ones that I've underlined. How many of them have a 5 in them? 1. So if there were other 5s, if like this last one in the yellow was a 5, you wouldn't count it. You don't care about it. You only care about the orange ones and what's going on with them. The last one is what's the probability that it's even given that it's not orange. So the ones that are not underlined are the not orange ones. So what's my total number of outcomes? 3. Now in just those 3, how many are even? 2. I do not care about this one right here that I'm pointing to, the 4, because it is orange. That's not part of my given information. All right, what we're going to do, I think, is we're going to finish up example 4, and then I'm going to leave you. There's one other example on the last page, example 5. You're going to do that as homework, and we'll start there when we come back, okay, so that we don't have to rush through. So example 4, do those 4 problems based on that table. Okay? Again, the first one is just a straightforward, regular probability problem. The other ones are conditional. All right, so this is a really basic example of how conditional probability would help you when you're analyzing data. So first thing we're going to see is what's the probability that somebody was satisfied with their care in this made up example. So what's the probability they were satisfied? Well, first, what's my total number of outcomes that I have here? 250. There's no condition put on this, so we're considering all 250. And out of those 250, how many people were satisfied? Okay, 210. And when you do 210 divided by 250 in the calculator, you get 0.84. So now what we're going to do is we're going to say, okay, well, that's great. How about what's the satisfaction rate given they had knee surgery? So I want to see, is knee surgery overperforming satisfaction or underperforming? This would, if you owned this clinic, that would tell you something. Maybe the knee surgeon is doing a great job, or maybe the knee surgeon is doing a terrible job, and we need to know that. Okay, so now I need given information. So what's my new total number of outcomes in this case? Okay, so that's the question. That's why we're doing this problem. That's why I put two table problems. So I want you to be good at reading tables. My given information is knee surgery. Knee surgery is the total number of outcomes. So I'm going to circle. All I care about now is the knee surgery row. So my total is not 210. Okay, it's a very common mistake. Okay, so I'm not calling out anybody. I'm not shaming anybody. Okay, that's why we do these problems. So knee surgery, whatever the given information is, that is the total. So I have 95 people. Out of those 95 people, how many of them are satisfied in that row? 75. Great job. Okay, so don't remember, mistakes are opportunities to learn, not opportunities to beat yourself up. So we got 0.7895. So the knee surgery satisfaction is underperforming the whole clinic. All right, so the next one says, what's the probability that the person had heart surgery given that they were dissatisfied with their care? Well, what's my total number of outcomes with the dissatisfied? 40. I'm going to circle the dissatisfied column. That's my total number of outcomes. So I'm only considering that column. So the total number of outcomes is 40. Out of those 40 that I circled that column, how many of them had heart surgery? 5. 5 out of 40. 5 out of 40 becomes 0.125. Fantastic. And then last but not least, what's the probability they were dissatisfied given that they had heart surgery, okay? So what's my total number of outcomes this time? Yes, that's the 50. Here's my heart people right here. These 50, I'm circling them. So the 50 people that had heart surgery, out of those, how many were dissatisfied? 5. So 5 out of 50 is 0.10, and that is reading my table for conditional probability.